Since we know now the fundamentals of Maple, let's use it to learn some physics and to understand how to solve physics problems quickly with less minutia and more comprehension. In this video, I go over 4 sample problems that one finds in introductory physics on vectors. Let's get started. Here's the problem that we're trying to solve. 2 forces pulling on this arm. We want a resultant force to be pulling purely in the horizontal direction with a magnitude of 12.8 newtons. In this problem, I'm going to assume that you have looked at the video on how to create vectors. To start, we're going to create a vector function which passes a magnitude and direction and breaks it up into the components of x and y. Since the angle may be in degrees, in fact we're expecting it to be in degrees, we need to come up with a function which converts it to radians. There is a function that does convert an angle from degrees to radians, but let's explicitly write out this function. Here we're going to create a and b by the function v, passing it the magnitude and the direction as a value in degrees. Unless we ask for a floating point approximation, Maple will return a precise answer. The physics says that if we add a to b as vectors, we should get a vector with a magnitude of 12.8 at an angle of 0 degrees. We can see the x and y components of the left-hand side. It must be equivalent to the x and y components of the right-hand side. There are only 2 variables unknown in this, so that we're going to solve this equation by using the solve command. There is our answer. The top one has a force of 8.8 newtons and the bottom has a force of 7.5 newtons. Here is a second problem. We're going to have a pilot fly to 4 different cities. Here is the direction and the angle in which, or the heading in which the pilot will fly. In flying, the assumption is the direct angle straight up is north, and we measure everything clockwise rather than counterclockwise. So we will need to convert those values. Our goal is we get to the 4th city, we want to get back to the original city. What is the distance in the heading that the pilot must fly to return back to the original city? So we play the same game as before. We use the fact that we have to write out our vector into their x and y components, and since the angle is going to be passed in degrees, we need the radian converter function. Each magnitude is passed as a distance, and the angle is initially measured in the 90 degrees, but then we subtract off the heading. This first vector is from Lincoln to Clarinda. This vector is from Clarinda to St. Joseph, and this one's from St. Joseph to Manhattan. The final leg is from Manhattan to Lincoln. It is a vector, again, with an unknown distance and an unknown heading. Here is the physics of the entire problem. Each leg must be added up so that the pilot returns to her origin. So we add all the vectors, vector sum, and it must end with 0, 0. Since this problem has been done precisely, i.e. with no floating point approximation, and we would like a numerical value, we don't care about the approximation, let's evaluate floating point of everything before we solve for the unknowns v sub ml and theta. We see that there are 2 solutions to this problem. Technically these are the same, but I'll use the second one because this distance is positive. This angle is to the west of north by 10 degrees. At this point we're going to actually use these solutions by assigning each of these variables their particular values. That's what the function assign does. Here is the code to make different cities and also the legs. The cities is made out of a function using the plot tools disk, and the legs are arrows from the plots library. When we display all the cities and arrows, this is our image for the travel starting from the origin back to Lincoln, Nebraska. And our third problem, again, it is a vector problem, but this involves momentum. The ball is traveling to the right, but is bouncing against the floor. It is going down, then bounces back up again. We're interested in the change in momentum of this basketball. Since it's a vector, we'll play exactly the same games using our v and rad formulas. In this problem, the basketball is traveling to the right at an angle 30 degrees to the vertical. So that's 30 degrees like that. So that's 270 degrees plus 30 degrees. So its initial momentum is some magnitude plus the 270 degrees plus the additional 30 degrees. Then it bounces up, which that bounce up is 90 degrees minus 30 degrees. So its final momentum is, again, we'll say assume it's the same magnitude in value, but at this direction. How do we find momentum? Momentum is moving mass, mass times velocity. This is the magnitude, so we need to put in the value for the mass, and we need to put in the value for the velocity. We're finally ready to do the physics, and the physics basically says what we want is the change in the momentum. That's the final momentum minus the initial momentum. That's the change. This is our answer. We would like to get a floating point approximation, which we do, and it turns out, not surprisingly, there's no change in the momentum in the horizontal direction. All the change in momentum is in the positive vertical direction. The final problem comes from the book that I love, Matter and Interactions. What we're going to do is create a 3D image of a cube with spheres at each corner of the cube and an arrow pointing from one corner to the corner directly opposite of it. We'll assume that each side has a length of 6 units. So we're going to restart, load the plots package, define sphere as something from the plots tool package, and place all the spheres at the 8 corners. I made a table labeled S from 1 to 8 where the location of each of the spheres are. I had to put in the components X, Y, and Z of every sphere, that's radius, and a particular color. There is our arrow coming from the plots package, starting at 00 and pointing to 666. We display all the spheres. It's a sequence of from sphere 1 to 8. We also include arrow A. We make sure the scaling is constrained, and that's what our image looks like, and you can rotate it around to see how it appears. I hope you found this video useful in understanding physics or doing physics problems. Please leave a comment below about the pace, since it is faster than I normally do it. Again, I'm assuming that you have gone through the Learning Maple series. Future videos will alternate between instruction and example problems on using Maple to understand physics.